Welcome! In this session, we'll explore the problem titled Minimum Adjacent Swaps for k consecutive ones. This is a fascinating problem that challenges our understanding of array manipulation and optimization techniques. Stay tuned as we break down the problem, discuss approaches, and analyze their complexities. In this problem, we are working with a binary array called nums, which only contains the numbers 0 and 1. Our task is to determine the minimum number of adjacent swaps needed to group exactly k consecutive 1s together in the array. A swap allows us to exchange two adjacent elements, which means we can move a 1-1 position at a time to bring it closer to another one. For example, if nums is 1, 0, 1, 0, 1, and k is 3, we need to find the least number of swaps required to form a block of 3 1s next to each other. The output will be a single integer representing this minimum number of moves. Let's look at an example to understand the problem more clearly. Suppose the input nums is 1, 0, 0, 1, 0, 1, and k is 2. This means we want to group two 1s next to each other with the fewest swaps possible. To do this, we can swap the 1 at index 3 with the 0 at index 2. This results in the array 1, 0, 1, 0, 0, 1. Since we only needed one adjacent swap to achieve the grouping, the output is 1. This example demonstrates how we focus on minimizing the number of moves while achieving the desired grouping. Here's another example. Suppose nums is 1, 0, 0, 0, 0, 0, 1, and k is 2. To group two 1s together, we need to move the 1 at index 6 leftwards, swapping it with each 0 along the way until it reaches index 1. This results in the array 1, 1, 0, 0, 0, 0, 0. In total, this requires 5 swaps, so the output is 5. Now consider a simpler case where nums is 1, 1, 0, 1, and k is 2. Here, the array already has two consecutive 1s, so no moves are needed. As a result, the output is 0. These examples highlight the variety of scenarios you may encounter and the importance of counting only the necessary swaps. To solve this problem effectively, there are a few important constraints and edge cases to keep in mind. First, the length of the array can be as large as 10⁻⁵, so the solution must be efficient and avoid brute force methods. The array contains only 0s and 1s, and the value of k is always less than or equal to the total number of 1s in the array, meaning a solution is guaranteed to exist. Special cases include arrays where all elements are 1s, as no moves are needed, or situations where k is 1, since a single 1 is already valid. Another challenging scenario arises when there are many zeros between the 1s, requiring careful planning to minimize the number of swaps. Efficient approaches often involve techniques like sliding windows or prefix sums to calculate the minimum swaps systematically. This ensures that we meet the problem's constraints while achieving optimal performance. To begin with, let's explore the brute force approach to solving this problem. The intuition here is straightforward. We try all possible positions where we can move the k1s together to form a consecutive subarray. For each of these positions, we calculate the number of swaps needed to bring the ones together. The process involves identifying all the indices of 1s in the array, then testing each possible configuration where k1s are aligned consecutively. For each configuration, we calculate the total swaps required and, ultimately, take the minimum of these costs as our answer. However, this approach has a major drawback. It has a time complexity of n squared, where n is the size of the array. This inefficiency arises because we repeatedly calculate alignment costs for overlapping groups, making it unsuitable for larger arrays. This limitation motivates the need for a more optimized solution that avoids redundant computations. Now, let's consider the optimized approach using the concept of the median. The key insight here is that the total number of swaps required to group k1s together is minimized when the ones are centered around their median position. The reason for this is rooted in mathematical properties. The median minimizes the sum of absolute differences, which corresponds directly to the number of adjacent swaps needed. To implement this, we first collect all the indices of 1s in the array. Then, we use a sliding window of size k over these indices to evaluate each possible group of k1s. For each window, the alignment cost is calculated by centering the group around the median index. Additionally, instead of directly summing distances, we apply an offset adjustment to simplify and optimize the calculations. This approach reduces the time complexity to O(n), as we efficiently compute the alignment cost for each sliding window. By leveraging this insight, we eliminate the inefficiencies of the brute force approach. Ultimately, the chosen strategy is the optimized approach using the median, and this decision is driven by its significant performance advantages. While the brute force method is conceptually simpler, its O(n) squared complexity makes it computationally prohibitive for larger input sizes. In contrast, the median-based approach achieves linear complexity, O(n), making it highly scalable. This is particularly important given the problem's constraints, where n can go up to 10 to the power of 5. The trade-offs further highlight the strengths of the optimized approach. Although it may require deeper mathematical insight to implement, it handles large arrays efficiently without compromising correctness. By centering the analysis around the median, this method strikes an ideal balance between computational efficiency and the ability to handle the problem at scale, making it the clear choice for this scenario. In this problem, we are given an array of integers consisting of only 0s and 1s, and our task is to move exactly k1s together into a consecutive subarray. The challenge is to find the minimum number of adjacent swaps required to achieve this. A swap means exchanging the positions of two neighboring elements in the array. To solve this, we can start by considering a brute force approach. This involves iterating through all possible subarrays of length k. For each subarray, we calculate the cost of moving all the ones into this subarray. By comparing the costs for all possible subarrays, we can determine the minimum number of swaps required to meet the goal. However, this approach is computationally expensive, as it examines all possible starting points for the subarrays of length k and recalculates the cost for each one. The brute force method requires calculating the cost of moving ones into each candidate subarray. This involves summing up the number of swaps needed for all 1s outside the target subarray to bring them into it. Once we compute the cost for a specific subarray, we repeat the calculation for every possible subarray of length k and keep track of the minimum cost encountered. To optimize this process and avoid redundant computations, we can use a sliding window approach. This technique allows us to efficiently calculate the cost by focusing only on the indices of the 1s in the array. First, we create a list of these indices, called positions. For example, if the array is 1, 0, 1, 0, 1, the positions array will be 0, 2, 4. Then, instead of brute forcing through the entire array, we use this list to identify groups of k1s and calculate their costs more efficiently. Next, we calculate the cost of swaps for each group of k indices from the positions array using a key optimization, the median. The median serves as the optimal center for the target subarray, as it minimizes the sum of absolute distances. This is because the median balances the movement of elements on both sides, leading to the least number of swaps overall. For instance, if the indices of the ones are 0, 2, 6, the median is 2. The cost to move all the ones to be around the median is calculated as the sum of absolute differences, abs 0 to 2 plus abs 2 to 2 plus abs 6 to 2, which equals 6. Using this approach, we calculate the cost for each sliding window of k indices in the positions array and update the minimum cost as we progress. The key insight here is that using the median to determine the optimal center significantly reduces the complexity of calculating costs. This eliminates the need for exhaustive recalculations for every subarray, as would be required in the brute force approach. Additionally, the sliding window technique ensures that we can efficiently evaluate each group of k indices without redundant computations. Another important optimization is pre-processing the array to extract the indices of all 1s. By focusing only on these indices, we reduce the problem size from the length of the entire array to just the number of 1s. This is especially beneficial for sparse arrays where the number of 1s is much smaller than the array size. To implement this approach, we rely on two main data structures. First, we use an array called positions to store the indices of all 1s in the input array. This helps us efficiently identify potential subarrays of k1s. Second, we use a sliding window to iterate over groups of k indices in the positions array. This allows us to calculate the cost of swaps dynamically as the window moves, avoiding redundant computations. For complexity analysis, the pre-processing step to create the positions array takes O(n), where n is the size of the input array. The sliding window operation involves iterating through the positions array, which has a size of m, the number of 1s, and calculating costs for each window of size k. This gives a time complexity of O, m asterisk k. Overall, the time complexity is O, n plus m asterisk k, and the space complexity is O, m, as we only store the indices of the 1s. When solving this problem, it's important to handle a few edge cases. First, if the array contains only zeros, there are no 1s to move, so the answer is simply 0 swaps. Second, if the array consists entirely of 1s, no swaps are needed regardless of the value of k, since all the 1s are already together. Third, if k exceeds the total number of 1s in the array, it becomes impossible to form a subarray of k consecutive ones. In such cases, the solution should explicitly handle this scenario by returning -1 to indicate that the goal cannot be achieved. By addressing these edge cases, we ensure that the algorithm is robust and handles a wide range of input scenarios correctly. This implementation solves LeetCode problem number 1703, minimum adjacent swaps for k consecutive ones, using a prefix sum and sliding window approach for efficiency. The algorithm begins by collecting the indices of all ones in the array, as the positions of zeros are irrelevant for this problem. Next, it constructs a prefix sum array of these indices to facilitate quick calculations of sums over any subarray of 1 indices. The main logic involves iterating over all possible subarrays of size k within the 1s_indices list. For each subarray, we compute the median position, as aligning the 1s around the median minimizes the number of swaps. Using the prefix sum array, the algorithm calculates the total movements required to align the 1s around the median efficiently in O(1) time for each window. Finally, the algorithm keeps track of the minimum swaps across all possible subarrays of size k and returns the result. This approach ensures an efficient solution with a time complexity of O(n), where n is the length of the input array, making it well-suited for larger inputs. Here, we begin by importing the necessary Java utilities and defining our class and method. The goal of the min-moves method is to calculate the minimum number of adjacent swaps needed to group k consecutive ones in the given binary array. First, we need to identify the indices of all the ones in the array. This is accomplished using a loop where, for every index in the array, we check if the value is 1. If it is, we add its index to a list called ones indices. This gives us a list of positions where each one is located in the array. Next, we create a prefix sum array to facilitate sliding window calculations. The prefix sum array is built iteratively, where each element is the cumulative sum of indices of ones up to that point. This will help us quickly calculate the sum of any subarray of ones within the ones indices list. Finally, we initialize a variable min_swaps to store the minimum number of swaps, setting it to the maximum possible value at the start. We then iterate over all possible sliding windows of size k within the ones indices list. For each window, we calculate the median index, which will serve as the target position for gathering the ones. To compute the total moves required to gather k ones around the median, we calculate the sum of moves needed for the ones to the left of the median and the ones to the right. The left moves are calculated as the difference between the prefix sum at the median and the prefix sum at the start of the window. Similarly, the right moves are determined by subtracting the prefix sum just after the median from the prefix sum at the end of the window. These values represent how far the ones need to travel to align with the median. We then adjust for the alignment of the median itself, accounting for its contribution to the total moves based on the window size. This is done using the formula provided, which ensures that the calculations are centered around the median index. Finally, we update the min_swaps variable to store the minimum value between the current min_swaps and the calculated moves for this window. After examining all possible windows, the method returns the minimum number of swaps required. This approach leverages the properties of the median and prefix sums to achieve an efficient solution. We begin with the array nums equals 1, 0, 0, 1, 0, 1, and k equals 2. The first step is to identify the indices of all the ones in the array. These indices are stored in the array ones_indices, which comes out to be 0, 3, 5. Next, we create a prefix sum array from ones_indices to make calculations more efficient during the sliding window process. We start with a prefix_sum array initialized to 0. Then, we add cumulative sums iteratively, adding 0 results in 0, 0, adding 3 gives 0, 0, 3, and finally, adding 5 produces 0, 0, 3, 8. With this setup, we can now calculate the minimum number of swaps needed by employing a sliding window of size k equals 2. To compute the minimum swaps, we slide a window of size k equals 2 over 1's underscore indices. For the first window, starting at index I equals 0, the median position is calculated as mid equals 0 plus 2 / 2 is equal to 1, which corresponds to 1's underscore indices, 1 equals 3. The left moves, or the total distance to align the ones before the median, is computed as prefix underscore sum, 1, prefix underscore sum, 0, equals 0. The right moves, or the distance for the ones after the median, is prefix underscore sum, 2, prefix underscore sum, 1 plus 1, equals 3. Adjusting for the median alignment gives us moves equals 3 to 0, 3 asterisk, 2 / 2, plus 3 asterisk, 2 to 1, / 2, equals 1. Thus, min underscore swaps is updated to 1. For the second window, starting at I equals 1, the median is mid equals 1 plus 2 / 2 is equal to 2, corresponding to 1's underscore indices, 2 equals 5. The left moves become prefix underscore sum, 2, prefix underscore sum, 1 equals 3, and the right moves are prefix underscore sum, 3, prefix underscore sum, 2 plus 1 equals 5. After adjustment, moves equals 5 to 3 5 asterisk, 2 / 2 plus 5 asterisk, 2 to 1, / 2, equals 1. The minimum swaps remain at 1. Thus, the output for this example is 1. In the second example, nums equals 1, 1, 0, 1, 0, 0, 1, 1, and k equals 3. First, we identify all indices of 1's, which gives us 1's underscore indices equals 0, 1, 3, 6, 7. Next, we build the prefix sum array starting from 0. Adding 0 results in 0, 0, adding 1 gives 0, 0, 1, adding 3 produces 0, 0, 1, 4, adding 6 gives 0, 0, 1, 4, 10, and finally, adding 7 results in 0, 0, 1, 4, 10, 17. With the prefix sum array ready, we proceed to slide a window of size k equals 3 over the 1's underscore indices array to compute the minimum swaps. For the first window, starting at I equals 0, the median position is mid equals 0 plus 3 / 2 is equal to 1, which corresponds to 1's underscore indices, 1 equals 1. The left moves are computed as prefix underscore sum, 1, prefix underscore sum, 0 equals 0, and the right moves are prefix underscore sum, 3, prefix underscore sum, 1 plus 1 equals 4 minus 1 is equal to 3. After adjusting for median alignment, moves equals 3 to 0, 1 asterisk, 3 / 2 plus 1 asterisk, 3 to 1, / 2 equals 2. The minimum swaps are initialized to 2. For the second window, starting at I equals 1, the median is mid equals 1 plus 3 / 2 is equal to 2, corresponding to 1's underscore indices, 2 equals 3. The left moves become prefix underscore sum, 2, prefix underscore sum, 1 equals 1, and the right moves are prefix underscore sum, 4, prefix underscore sum, 2 plus 1 equals 10, 4 is equal to 6. After adjustment, moves equals 6 to 1 and 3 asterisk, 3 / 2 plus 3 asterisk, 3 to 1, / 2 equals 1. The minimum swaps are updated to 1. For the third window, starting at I equals 2, the median position is mid equals 2 plus 3 / 2 is equal to 3, which corresponds to 1's underscore indices, 3 equals 6. The left moves are calculated as prefix underscore sum, 3, prefix underscore sum, 2 equals 4 minus 1 is equal to 3, and the right moves are prefix underscore sum, 5, prefix underscore sum, 3 plus 1 equals 17 to 10 is equal to 7. Adjusting for median alignment, we get moves equals 7 to 3 6 asterisk, 3 / 2 plus 6 asterisk, 3 to 1, / 2 equals 1. The minimum swaps remain at 1. Thus, the output for this example is 1. In the third example, nums equals 1, 0, 1, 0, 1, 0, 1, and k equals 4. We start by identifying the indices of all 1's in the array, resulting in 1's underscore indices equals 0, 2, 4, 6. Next, we construct the prefix sum array, starting from 0. Adding 0 produces 0, 0, adding 2 gives 0, 0, 2, adding 4 results in 0, 0, 2, 6, and finally, adding 6 produces 0, 0, 2, 6, 12. With the prefix sum array ready, we now slide a window of size k equals 4 over the ones underscore indices array to determine the minimum number of swaps. For the first window, starting at I equals 0, the median position is mid equals 0 plus 4 / 2 is equal to 2, which corresponds to ones underscore indices, 2 equals 4. The left moves are calculated as prefix underscore sum, 2, prefix underscore sum, 0, equals 2 minus 0 is equal to 2, and the right moves are prefix underscore sum, 4, prefix underscore sum, 2 plus 1, equals 12, 6 is equal to 6. Adjusting for the median alignment gives moves equals 6 to 2 4 asterisk, for / 2, plus 4 asterisk, 4 to 1, / 2, equals 4. Since this is the only window possible, the minimum swaps for this example is 4. Thus, the output is 4. In this solution, we aim to calculate the minimum number of adjacent swaps required to gather k consecutive ones in the given array. To start analyzing the time complexity, we first gather the indices of all the ones in the array. This is done using the enumerate function, which iterates through the entire nums array of size n. Since we visit each element exactly once, this step takes n time. Next, we create a prefix sum array using the indices of the ones. If m represents the total number of ones in the array, constructing the prefix sum array involves iterating through the ones underscore indices array, which has size m. This operation is performed in m time. Together, these two steps form the foundation of our algorithm, ensuring we pre-process the data efficiently. Now, we use a sliding window of size k to compute the minimum number of swaps. The sliding window moves across the ones underscore indices array to evaluate all valid windows of size k. Specifically, the outer loop runs mk plus 1 times, which is the total number of possible windows in an array of size m. For each window, we calculate the number of moves required to gather the ones in that window using prefix sums. The prefix sum array allows us to perform these range sum calculations in time, ensuring the inner operations are highly efficient. Because the sliding window iterates at most m times in the worst case, this step has a time complexity of m. Combining all the steps, the total time complexity becomes n for gathering indices, m for the prefix sum array, and m for the sliding window. This results in an overall time complexity of n plus m. Since m is at most n, the worst case complexity simplifies to n. The space complexity of this solution can be broken down into 3 components. First, we store the indices of all ones in an array called ones underscore indices. In the worst case, where the entire array consists of ones, this array will have a size of m, which is the total number of ones. Thus, the space complexity for this step is m. Second, we create a prefix sum array to facilitate efficient range sum calculations. The size of this array is m plus 1 because it includes one extra element for the initial 0. This also contributes m to the space complexity. Finally, we use a few additional variables such as min underscore swaps, median, left underscore moves, and right underscore moves, all of which require constant space. Therefore, these variables contribute 1 to the space complexity, which is negligible compared to the arrays. When we combine the space requirements, the total space complexity is dominated by the ones underscore indices and prefix underscore sum arrays, each of which is m. Since m is at most equal to n, the worst case space complexity is n. To put this in perspective, a naive or brute force approach would involve generating all possible subarrays of size k and calculating the number of swaps for each subarray. This method would require iterating through all possible combinations, leading to a time complexity of n asterisk k in the worst case. In contrast, our optimized approach avoids this inefficiency by leveraging the indices of ones and using prefix sums to perform efficient range sum calculations. The sliding window ensures we reuse previously computed results for overlapping subarrays, reducing the time complexity to n, and making the solution far more efficient. This solution also performs well under different scenarios. In the best case, if the array already contains k consecutive ones, the sliding window quickly computes the result, and the time complexity remains O(n). For random distributions of ones, the pre-processing step and sliding window approach ensure that the average case complexity is also O(n). Even in the worst case, where the entire array consists of ones and we need to evaluate all possible subarrays of size k, the algorithm still runs in O(n) time. This consistency across best, average, and worst-case scenarios highlights the robustness of the solution, as it avoids excessive computation while maintaining optimal performance. Finally, let's confirm the mathematical proof behind the complexity. For the time complexity, we sum up the O(n) pre-processing step and the O(m) sliding window operations to get O(n) plus m. Since m is at most equal to n, this simplifies to O(n). For space complexity, the main contributors are the ones underscore indices and prefix underscore sum arrays, both of which require O(m) space. Since m is at most n, the space complexity is O(n). These results demonstrate that the solution is optimal in both time and space, making it highly efficient for solving the problem of finding the minimum adjacent swaps for k consecutive ones in an array. When working on this problem, there are a few common mistakes to watch out for. One of the most frequent errors involves misidentifying the cost of swaps. Some might assume that the number of swaps needed is simply equal to the number of zeros, or non-ones, in the target range. However, this doesn't account for the positions of the ones and how far they are from the target window, which is critical for minimizing swaps. Another mistake is using a brute force approach with nested loops to calculate swaps for every possible window of size k. This results in an O(n) squared time complexity, which quickly becomes inefficient as the input size grows. Instead, methods like sliding windows or prefix sums are much more optimal. Finally, it's essential to handle edge cases correctly. For example, if the array is entirely made of ones, no swaps are needed, and if it's entirely zeros, the problem may not be valid at all. Neglecting to account for these scenarios can lead to incorrect results or even runtime errors. Another common mistake is implementing the sliding window approach incorrectly. When updating the window, it's crucial to adjust the counts properly as the window moves. Failing to do this can lead to skewed results, particularly when dealing with overlapping segments. Additionally, some may overlook the constraints on input size. For example, when n is very large, such as greater than 10 to the power of 6, solutions that require excessive memory might fail. This is especially true if you're using data structures like prefix sums but don't manage memory efficiently. Always ensure that both your time and space complexities are well suited to the problem's constraints. Now, let's consider some insights that are particularly relevant for interviews. This problem is a great example of pattern recognition. It tests your ability to identify patterns, such as grouping elements and minimizing operations, which are common in array manipulation. It's also an opportunity to demonstrate your ability to optimize brute force solutions, particularly by using sliding windows effectively. Interviewers often assess whether you can recognize when sliding windows are appropriate. Additionally, it's vital to ask clarifying questions, such as whether k is guaranteed to be valid, that is, whether there are at least k ones in the array. Handling edge cases is another key discussion point. Be ready to explain how you would approach situations where the array has no ones, is entirely ones, or is very small. Finally, you may be asked to discuss trade-offs between different approaches, such as sliding windows versus prefix sums, and explain which is more suitable under certain constraints. This problem also shares similarities with other common LeetCode questions, which can help you recognize useful techniques. For example, in LeetCode 1004, max consecutive ones 3, you flip zeros to maximize a window of consecutive ones, which involves similar trade-offs. In LeetCode 1248, count number of nice subarrays, the focus shifts to counting subarrays with specific constraints, but sliding windows play a critical role there as well. LeetCode 424, longest repeating character replacement, requires optimizing a window to minimize replacements while satisfying constraints, which is another variation of optimizing within a window size. Finally, LeetCode 1493, longest subarray of ones after deleting one element, also deals with manipulating ones in an array to achieve a specific outcome. Studying these problems can deepen your understanding of how to approach variations of this challenge. There are also alternative approaches you might consider, each with its own trade-offs. One option is the prefix sum approach, where you compute a prefix sum of ones to efficiently calculate the number of ones in any range. While this can speed up the calculation, it requires additional memory for the prefix sum array, which may be a concern for very large inputs. Another approach is the sliding window method, where you maintain a window of size k and dynamically adjust the counts as the window moves. This approach minimizes memory usage but requires careful implementation to avoid mistakes. Lastly, there's the greedy approach, which involves identifying the median position of the ones and calculating the swaps needed around it. This is highly efficient in specific scenarios but can be harder to generalize for all inputs. Choosing the right method depends on the constraints and requirements of the problem at hand. Great job making it to the end. We reviewed how to solve the problem minimum adjacent swaps for k consecutive ones using efficient techniques like sliding windows and prefix sums. Remember to practice these approaches to strengthen your problem-solving skills. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!